Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week on the podcast, I'm excited to present a series of interviews exploring the emerging field of differential privacy. Over the course of the week, we'll dig into some of the very exciting research and application work happening right now in this field. In this episode, I'm joined by Nicolas Papernot, Google PhD Fellow in Security and graduate student in the Department of Computer Science at Penn State University. Nicolas and I continue this week's look into differential privacy and machine learning with a discussion of his recent paper, Semi-supervised Knowledge Transfer for Deep Learning from Private Training Data. In our conversation, Nicolas describes the private aggregation of teacher ensembles, or pate, model proposed in his paper, and how it ensures differential privacy in a scalable manner that can be applied to deep neural networks. We also explore one of the interesting side effects of applying differential privacy to machine learning, namely that it inherently resists overfitting, leading to more generalized models. Thanks once again to George & Partners for their continued support of the podcast and for sponsoring this series. George & Partners is a venture capital firm that invests in growth stage business software companies in the US and Canada. Post-investment, George works closely with portfolio companies to accelerate adoption of key technologies, including machine learning and differential privacy. To help portfolio companies provide privacy guarantees to their customers, George recently launched its first software product, Epsilon, which is a differentially private machine learning solution. You'll learn more about Epsilon in my interview with Georgian's Chang Liu later this week, but if you find this field interesting, I'd encourage you to visit the Differential Privacy Resource Center they've set up at gptrs.vc/TWiMLAI. And now, on to the show. All right, everyone, I am on the line with Nicolas Papernot. Nicolas is a Google PhD Fellow in the Department of Computer Science and Engineering at Penn State University. Nicolas, welcome to This Week in Machine Learning and AI.
Thank you, Sam. I'm very happy to be here.
I'm very happy that we have finally connected. We have been trying to get this conversation going for a while now. So I'm also really interested in digging into differential privacy, which is, I think, an area of very interesting promise with regards to machine learning and AI and the intersection with privacy. But before we jump into that, why don't we take a few minutes and have you introduce yourself to the audience and tell us how you got involved in machine learning and AI?
For sure. Yeah. So I joined Penn State about 4 years ago, just coming in from France, where I'm from, after finishing up my undergrad. And I joined this lab here at Penn State, headed by Professor Patrick McDaniel, who's a security researcher. And at that time, it had been very recently demonstrated that state-of-the-art vision models were vulnerable to small perturbations of their inputs, which researchers called adversarial examples. And so that was something very interesting to us, because from the machine learning perspective, adversarial examples have a lot of implications, because they mean that models don't generalize as well as we expected them. And at that point in about 2014, machine learning models were starting to get pretty good, sometimes outperforming humans at some of the tasks. And so it was already a surprising fact from the machine learning perspective that models are so susceptible to these small perturbations. But for us, from the security perspective, the implications were much more serious. And that sort of attracted my interest in machine learning, especially when you see applications to transportation, to the energy sector, with machine learning being able to sort of optimize some of the decision making that's traditionally done by humans, or with healthcare. All of these domains, it is clear that machine learning is being applied more and more widely in these critical applications. And so as a security researcher, when the technology becomes so pervasive, you, of course, consider all the potential implications as it becomes a target for adversaries, and try to envision how adversaries will try to manipulate these systems. And so adversarial examples were sort of the first threat vector that I've considered against machine learning, and from there branched a lot of interests more widely with anything related to machine learning, and including a little later, about 2 years later, in differential privacy.
All right, awesome. Maybe a great place to start is for you to talk a little bit about differential privacy, what it means, and what some of the objectives are.
So differential privacy is essentially a framework for understanding where the privacy information may leak in algorithms. And it's also a framework for preventing this information from leaking from the algorithms manipulating the data. So at a very high level, you can think of differential privacy as defining two worlds. So you have assumed that your application is collecting data about a particular population. And so you would have two worlds, one world where you would have all of the people in the population, and a second world where you would have just one person missing from this population. And so what differential privacy requires is that the algorithm that you're going to run on the data should not have a statistically different behavior, whether you are in the first world or in the second world. And what that means for all of the users in the population that you're learning from is that the behavior of the algorithm is not going to reflect any specific information about a particular user, but rather it's going to only reflect general patterns that are found across the population. And so this is why differential privacy has become one of the gold standards in privacy, and probably the most widely applied. Is because this definition does not make any assumptions about the adversary. So essentially that means that regardless of the knowledge that the adversary has, regardless of what attack techniques the adversary will think of, the guarantee that you have provided that the behavior of the model does not overfit to specific people in the population will stand in the future. And so differential privacy has been applied to many algorithms. For instance, it was applied to databases to answer queries from SQL databases while protecting privacy. And more recently, it has been applied a lot to machine learning, and especially deep learning in the last couple of years. And there's a really natural, I would say, synergy between machine learning and differential privacy. And the way I like to think about it is that differential privacy is a way to give a cost, to put in a value on some of the failures that machine learning may have. So when you think about it, overfitting to a particular training point is likely to violate privacy. So if you memorize the information about a particular training point that you have in your set, then whoever contributed this training point may not be able to retain its privacy because the model's behavior will very likely be largely influenced by this specific training point. And so with differential privacy, you're essentially saying during the learning process, if you overfit to this particular point, you will have to pay this particular amount of privacy. And so you have this connection between privacy and achieving generalization, where in a way privacy is a worst case guarantee and generalization is more of a mean average case metric. But when you have privacy, you are helping the model in a way to behave better.
Does it apply equally well across different types of models and algorithms, meaning traditional machine learning algorithms, relative to deep learning algorithms and neural networks?
Yeah, differential privacy has been applied to all sorts of machine learning models, starting with very simple things like logistic regression, and all the way to deep learning more recently. What happens is that you can make most algorithms differentially private by randomizing their behavior. So, for instance, if you're learning a neural network, you have several ways that you can introduce, you can guarantee that you're providing differential privacy. You can perturb the inputs. So if you have a data set, you can randomly flip some of the labels, randomly perturb some of the inputs in a way that would provide differential privacy. You can also perturb the model's parameters. So that would imply, for instance, when you're applying stochastic gradient descent to learn a model, you would take the gradients of the model with respect to using the training data, and you would add some noise to these gradients before applying them. And that would result in a model whose parameters provide differential privacy. And then you have a third way of achieving differential privacy, which is by perturbing the output of the model itself. And so essentially, you can adapt all learning algorithms to introduce privacy by randomizing either their input, the model itself, or their output. And the question is whether you can calibrate this random behavior to be able to provide, on one hand, strong privacy guarantee. So that requires that you analyze, in the worst case settings, how the training data will influence your predictions. And on the other hand, so if you once you have this guarantee of privacy, you also want to make sure that the model is going to perform well. So you want to calibrate the noise so that it is large enough to protect the privacy of the training data, but also small enough that it will not harm your performance. And I guess what has been very exciting in I would say the last year or two, is that we are seeing different scenarios where we can calibrate the noise in a way that it doesn't harm the performance. And actually, providing privacy can allow us to also achieve at the same time very strong performance. And again, that it is because there is this synergy that you can exploit between privacy and utility. If you think about it, if a model is making a prediction that is very likely to be correct, it means that this prediction is supported by patterns found in the training data that are patterns that are widely found in this training data.
Right.
And so it also means that this prediction does not depend on specific points in the training set. And as a consequence, you can provide strong privacy for that prediction. And so, yeah, this is something that I'm very excited about, because that would mean that we would be able to switch from a setting where privacy is often presented as something that you need to trade off with utility, to a setting where you can achieve privacy with very limited or no impact on performance. So I would say we're sort of in between these two right now, where for most algorithms, we're still in the first scenario where we have to trade off some utility to get privacy, but whereas in some cases, we are moving to the second scenario. And that's extremely exciting for the field, because it means that differential privacy would be more likely to be applied in all sorts of algorithms.
Right. And so just to capture that last point, the idea there is that traditionally we've got this trade-off between model generalization and overfitting, and creating models that overfit is one of the biggest challenges in employing these models, beyond the training data and against real world data. But differential privacy, because its goal is, highly aligned with generalization, it also serves to kind of fend off overfitting.
Right. So just to be clear, again, generalization and privacy are different things. So generalization is a metric that looks at the average performance, and privacy is a metric that looks at the worst case performance. So you do have this direction where when you achieve privacy, you help towards generalization, but the other way around doesn't hold. So if you have generalization, that doesn't guarantee privacy because, again, privacy is a worst case setting. But it is true that providing privacy is eventually one direction for improving the generalization of learning algorithms. That is definitely true.
Okay. So maybe can you tell us a little bit about your specific research in this area? Do you have any recent papers on this that we can maybe talk a little bit about?
Yeah. So my research in differential privacy and machine learning has focused on a particular approach, which is called pate. So the name is French, even though it's hard to believe I didn't come up with the name on my own. But it stands for private. It stands for private aggregation of teacher ensembles.
Okay.
And so the idea for this approach is that we'd like to achieve privacy and a rigorous form of privacy, so differential privacy, but also at the same time be able to explain why we achieve this privacy in a very intuitive way. And the idea is that rather than having this mysterious guarantee that you provide the privacy, you're able to convey an intuition why the approach protects the privacy of the training data. That is very useful because, again, differential privacy often comes with its set of theorems. You need to prove things in a language that's not necessarily easy to understand for a lot of people unless they have lots of experience in that area. So basically the approach looks at the training data and begins by partitioning the training data. So if you have one set of data, you'll create n partitions from this set of data, and the only constraint is that these have to be real partitions so that there is no overlap between the subsets of data. And so from each of these subsets, what you do then is that you learn a machine learning model independently on each of these subsets. And the nice thing is that you can learn these models using any learning algorithm. So if you want to use a decision tree, if you want to use logistic regression or even deep learning, that's okay. And so at this stage, you have learned n different models on your training data in a completely independent way. So the models are looking at different subsets of the training data, and when they all make a prediction on a particular input, if they all agree on this prediction, you know that this prediction was made from a pattern that is general across the data and not about a specific partition of the data. And so this is where the intuitive privacy guarantee comes from, because, again, when we ask all of these models, and we call these models teachers, so when we ask all of the teachers to make a prediction, if 95% of them all make the same prediction, we know that this is a prediction that results from a general pattern from the data. And so if we take as the common answer of the teachers the prediction that is assigned the most number of votes, so the one that the majority vote among the outputs of the teachers, then we have this intuitive privacy guarantee that, again, this is a prediction that results from a consensus. The question now is, how do we add noise to this mechanism in order to be able to prove that it provides a rigorous guarantee in the sense that it provides differential privacy? And so what happens there is that you introduce random noise at the outputs of the teacher. So you randomly perturb a subset of the labels predicted by the teachers, and then afterwards you take you make the aggregation. So what this means is that the aggregation is not performed on the true votes of the teachers, but on the randomized votes of the teachers, and using the noise and by calibrating this noise according to the privacy guarantee strength that we want to achieve, then we're able to guarantee that essentially every time the teachers make a prediction, this prediction is made with a certain level of privacy. And so in differential privacy, there is a particular parameter called epsilon, which essentially measures how indistinguishable the two worlds that I mentioned earlier are. And so the smaller the value of epsilon is, the stronger the privacy guarantee is. Mm-hmm. And essentially, using this mechanism, we can provide a specific epsilon value for each of the queries that we make to the teachers. So then we have another step in the approach, because at this point, every time the teachers respond, they are going to reveal very little private information, but over time, this private information is going to accumulate. And so you would have to bound to fix the number of queries that the teachers answer. And so what we do is that we use the teachers to supervise the training of an additional model called the student model. And so this student model is going to learn from the teachers by sending them unlabeled inputs and training on the private label that the teachers are returning as an aggregate. And so essentially what this does is that it transfers the knowledge that the ensemble of teachers learned from the sensitive data in a privacy-preserving way into the student model. And so once the student model is trained, and we only need a fixed number of labels to train the student, we can release the student as the model that makes predictions, and that student model can answer as many predictions as we want. The cost in terms of privacy is fixed. And what that means as well is that if an adversary tries to inspect the parameters of the student model or to look at the predictions of the student model, in the worst case, what it can recover is the private labels that the student learned from, that it received from the teachers. And because we provided these labels with differential privacy, we can guarantee that there will be no more private privacy leakage than what is allowed by the guarantee that we were able to prove mathematically. And so once we have this student, this is essentially the end product. This is what we want to release, to deploy in our application. And then we can also simply just discard all of the teachers, all of the training data. We don't need it anymore to use the student. And so that's the approach that we've been working on. And this is where sort of the idea of having a synergy between privacy and utility came, and that I was describing earlier in our conversation, is that you can see here clearly that the utility of a label is reflected by the number of teachers that agree on that prediction. So when you have lots of teachers, almost all of them agree on the prediction, it's very likely to be a correct prediction. And because they all agree, that means that you can perturb their answers a lot. You can introduce lots of random noise and still provide, and that will result in a very strong privacy guarantee. And so that's how we're able to make the synergy between privacy and utility explicit with the pate approach. And that's extremely exciting. And we've tested it on a few data sets, and it really gives you some very high utility at very strong privacy guarantee. So I'm very excited to see where we can push that technique in the future.
You may have just answered one of the questions that I had, but to kind of take a step back, you've got this 3-step approach to creating privacy guarantees using this this model, this approach. The first is you partition the data set and you train an ensemble of these teacher models, and these can be mixed models, so they don't have to be uniform. You then use the predictions of these teacher models in kind of a consensus manner to determine an intermediate prediction, which is then used to train a student. The student model that you're creating is kind of your ultimate model that you deploy. And because of the process that you have gone through, there are some privacy guarantees that you have made around the student, and it's also impervious to long-term data leakage. Is that correct in a nutshell?
Right.
Before I go into my questions.
Yeah, that's exactly it.
Okay. So one question that I had was at the second step where you're perturbing the outputs of your teacher models. Would you say that perturbation increases the privacy that is attained, or is it simply required to make the privacy guarantees? Does that question make sense?
It makes a lot of sense. It is required that you perturb the output of the teachers. It is not possible to achieve differential privacy without introducing some randomness in the algorithm's behavior at some point. And that's because differential privacy, basically, if you don't have this randomness, you would not be able to learn anything meaningful, because the definition would prevent you from learning anything from any point. And so this randomness is what allows.
Can you elaborate on that? Meaning the definition of differential privacy?
Right, because if you want to have this guarantee that the behavior of the algorithm is identical on the two worlds, this guarantee has to be statistical. It has to, if it were deterministic, you would not be able to learn anything, because the algorithm could not learn anything from any of the training points. And so that's why you have this randomness, because it introduces this ambiguity. When the adversary sees the same prediction or a different prediction from the algorithm, it is not able to know whether that change in the prediction resulted from a change in the training data or a change in the outcome of the random noise that was sampled.
Right. And so I guess I'm asking more is maybe like a hair splitting or semantic kind of question, but I'm really asking it as a path to truly understand what's happening here. The goal is, you could argue that the goal is privacy as opposed to differential privacy, right? Differential privacy provides a guarantee of privacy, but what I ultimately want is privacy. And what I'm trying to get at is, if we didn't do steps 2 and 3, it strikes me that there's an argument that we've already, created some degree of privacy just by doing the partitioning of the data and this kind of ensemble consensus approach. And I'm wondering if that is in fact the case, or, is it perhaps the case that no, not really, we haven't even achieved any measure of privacy with doing that, or it's very little. Is there anything that you can say about the degree of privacy that we've achieved just in that first step, as opposed to, the differential privacy specific pieces that the second and third steps add?
Yeah, for sure. I mean, you're basically coming at one of the design goals of this approach is that we want to be able to provide an intuitive notion of privacy, in addition to providing this rigorous definition of differential privacy. Mm-hmm. And so you are right that if we only perform the ensembling and outputting the aggregate answer of this ensemble, that would provide some notion of privacy that is not differential privacy, but you could perceive it as a form of privacy. And that really drives at the fact that privacy is an extremely subjective notion, And so different people will have different expectations in terms of privacy, but it is true that the approach, even if you don't add noise or train the student, provides you with this intuitive definition of privacy. However, I want to be careful with that, because I would say that our intuition when we design algorithms to provide privacy is very, very often wrong, and it's hard to capture all of the ways which could result in a privacy leakage.
Is there an example that comes to mind of how the ensemble approach alone doesn't create the kind of privacy that we want?
Yeah, I'll give you an example with the ensemble, and then with a completely different application.
Okay.
With the ensemble, let's assume that you're sending a query to the ensemble, and exactly half of the teachers assign the label cat and half of the teachers assign the label dog. If you then change the training data of one of the teachers, which the adversary could do, and you run the same algorithm, so you trained the teachers and answer the same prediction, then because you change the training data of one of the teachers, in the worst case, you should assume that teacher will change its prediction. And so in cases where you have exactly the same number of votes for two classes, changing the predictions of one teacher might change the outcome of the aggregation, because it might make one class more likely than the other, or just invert the order of the classes. So essentially, if you don't have this noise, the prediction of the ensemble can depend on the predictions of a single teacher, and so you don't have this consensus part where you have this large, overwhelming consensus among the different models, which provide you this intuitive notion that you're having a very large agreement that reflects the fact that the pattern is general across the training data. And so that's why the noise provides privacy, because it makes these scenarios ambiguous and prevents the adversary from understanding whether the change in the prediction results from the change in the training data or from the noise. Another example of to sort of motivate differential privacy is that there are lots of ways that you can achieve intuitive notions of privacy, and one very common way is to anonymize the data. So to remove any part of the data that could be used to infer the identity of the people who contributed this data. And this has happened in the past. So there was a data set which was released by Netflix where they had anonymized the data, which was essentially ratings for movies and ratings from a large pool of users. And so they removed all of what they thought would be something useful to infer the identity of the persons who assigned these ratings. But then some researchers found later that if they perform what is called a linkage attack, so they use a second database, which in this case was the IMDb database, to sort of cross the records from the Netflix database with the records from the IMDb database, because the ratings were unique enough in both databases. They were able to link the records from the Netflix database to the records from the IMDb database, which is public. And so they were able to recover the identity of a lot of users in the Netflix database, which was supposed to be anonymous. And so that's just an example of why providing these notions of privacy that are intuitive is a good start, but it's not enough to claim success. And I'm not saying that we should not be anonymizing the data. It is a good practice to anonymize the data, but we shouldn't rely on it as the ultimate way to provide privacy. And so what is nice again about differential privacy is that the definition is robust to all these attacks that use auxiliary information, like was the case with the IMDb database. Anonymization did not take into account that the adversary would have access to this public information, which helps mount the attack. And so with differential privacy, you don't have this problem. So the adversary can have all this knowledge. It's not going to impact the strength of your guarantee. And so it makes it the definition is constraining in the sense that the analysis that you have to perform is extremely worst case. It's very constraining. But once you've managed to provide differential privacy, you're really providing a guarantee that is robust in the face of a lot of future attacks that people may come up with.
Can you elaborate on how differential privacy specifically applies in the case of this Netflix example you gave? In particular, the differential privacy we've talked about thus far has to deal with a model that I've created on some training data set, and the kind of result or product of this differential privacy process is call it a privacy robust model. In the case of the Netflix example you described, what Netflix provided that potentially got them into trouble was this data set, even though it was somewhat randomized. Is there a way how does differential privacy play here? Could differential privacy have been used to create a better anonymized data set for them to share? Or is differential privacy not applicable if you need to actually share your training data?
That's a very good question. So as I mentioned before, there are really three places where you can think of providing the privacy. It's at the input of the algorithm, in the algorithm, and at the output of the algorithm. Mm-hmm. And so there's several techniques to provide differential privacy at the input. One of the techniques that is easiest to get an intuition for is called local differential privacy, where the idea is that you're going to perturb the data itself. And so one easy example to think about it is, let's assume you're collecting data from a pool of users. And so you're going to ask each of these users to flip a coin. Mm-hmm. And depending on the outcome of that coin flip, they will do, if it's heads, they will respond with the true answer to your question. And if it's tails, they'll respond with a completely random answer. Mm-hmm. And so if you do this across a very large pool of users, because with what probability people will respond with the random answer or with the correct answer, you can still collect data that will be useful for you to extract statistics or to perform an analysis on. But each user that participated in this process can still have what is called plausible deniability, that they did not provide the correct answer. So if you ask any particular user, they could just tell you, I responded the random answer, and you have no way to verify that because you don't have access to the coin flip, that outcome that they had. Mm-hmm. And so that's a particular way where you can collect data from users and achieve differential privacy without training a model on top of that data first.
Meaning, so Netflix, in providing this data set, in addition to eliminating any personally identifiable information, they could have also randomized some number of the labels on the data set. And it sounds like doing so in such a way that didn't inherently change the statistics of the data set.
Right.
And
yeah, so for instance, they could have for each rating flipped a coin and depending on that output the real rating or a random rating, for just as an example.
And if I'm building a model using this data and I know that this is the case, or I suspect that this is the case, can I take advantage of that?
What do you mean by taking advantage of that?
Meaning, if I'm, if this is the Netflix prize, and their Netflix has published this data set, and I suspect that they've done this, or they've told me that they've done this, can I use that knowledge to increase the chance that I'll, win the prize, but, make my model better performing?
I don't think that would, having knowledge about the fact that they collected the data in a privacy preserving way would provide you any advantage in the competition. But what it does point out is a very nice property of differential privacy, is that once you've achieved differential privacy and you release statistics that are resulting from this differentially private process, any post-processing of the data maintains the differential privacy. So once you've achieved differential privacy, you can analyze the data as much as you want. You can train another model on the data, and the guarantee is still provided. So it holds in the face of post-processing, which is another very, very nice property of this definition.
Okay, and so then just to take a step back and be clear, this coin flip and substituting random data, is that in and of itself enough to give me a differential privacy guarantee for this data set?
Yes.
Oh, okay.
So it's called local differential privacy. There are some variants of it to improve the utility of the process, but yes, in short, and at a very high level, that is the idea that is sufficient to provide differential privacy.
Great. Okay. Awesome. And so then the third phase of the pate model that we talked about was training the student. And the idea with training the student model was that the student basically is trained on this aggregate or ensemble parent model, and the idea is that using the student provides you with a set of guarantees because the student never had any access to the underlying training data. Is that the right way to think about it, or is there? I feel like I may be missing a nuance here.
Yeah, it is mostly the right way to think about it. There are two components. So the one that you mentioned, that it did not have access to the underlying data, provides robustness to adversaries who would attempt to inspect the parameters of the model. The nice thing about training the student is mostly that it fixes the number of questions, the number of predictions that the teachers will answer. So if you could, in practice, if you were able to guarantee that no one will be able to inspect the teacher's parameters or to extract the teacher models, you could use the ensemble of teachers as sort of a differentially private API, which would respond to user queries, and each query would be provided with a certain privacy guarantee. But again, over time, as you answer more and more queries, you would accumulate a privacy budget that would become unreasonable, and eventually you would not be able to provide any meaningful guarantee with respect to your training data. And again, if as adversaries, and we're seeing this more and more, where attacks are able to extract some of the training data or some of the parameters of the model by only having access to its predictions. So if that is also possible, then we have to be worried that the adversary would be able to recover some information about the training data that the teachers had access to. And that's why training the student is very nice, because the student only has access to this limited set of labels from the teachers. We're able to guarantee first that the overall budget that we spent in terms of differential privacy is fixed. So once we've trained the student, we don't access the teachers anymore, so we don't perform any computation that depends on the sensitive data. And again, because the student was only trained on this private data, even if the adversary is very strong and able to recover the training data of the student, that data is not the sensitive data that we were protecting. So we have this strong guarantee in this case as well.
Okay. It sounds like a way to think about that is that we use the student for the same reason why your computer or your iPhone will start injecting delays if you get your password wrong for 3 times. It's to prevent someone from using a large number or infinite number of brute force attacks to attack the model or attack the password.
Yeah, I guess that's a way to think about it, is that once the adversary has access to the system and is able to make lots and lots of queries to it, so like in your example, trying to enter as many passwords to eventually figure out if that is the correct password, then yes, as the adversary makes a very large number of queries, eventually it is able to infer some information about the system, and so that's what the student protects against, because it disconnects the model that is predicting from all of the teachers that had access to this sensitive training data. And the reason that it's not as easy as preventing against someone using your phone to enter the password and eventually figuring it out is, so in that case you can introduce this delay, and that makes the attack much more impractical. But often what happens is that machine learning models are exposed through an API, through online or in a local network. And so essentially you could envision that the adversary would distribute its queries. And so that would make it very hard for the owner of the model to know whether a particular sequence of queries is an attack trying to find information about the model, or if it's just a set of legitimate users who are actually using the model as intended. And so you have this point where after you hit the sweet spot, the utility and the privacy of the model will start degrading. And so it's hard to give numbers, like guidelines for numbers. It really is a question of both the complexity of your models, which sort of indicates how much data you will need to train them, and also the complexity of the task, how many outputs there is in the task. And in our research, we've sort of tried different applications, different models with smaller tasks and tasks with hundreds of outputs. And the number of teacher will vary, in our case, between 100 and 5,000. So it really depends. If you have the data to support more teachers, then that makes your life easier. Mm-hmm. But again, the nice thing is that you're able to use any machine learning model. So once you have a model that works without privacy, if you have a lot of data, then you can sort of apply this framework quite easily by partitioning the data and just training your model several times on these different data sets. So that's the nice advantage about the approach.
Okay. And I don't recall off the top of my head in the case of, let's take the case of deep learning. I don't recall what the if training time is, linear in the, linear, sublinear, or superlinear in the number of training examples. But I'm wondering if you've done any work to look at like theoretical bounds on the relative training time using a partitioned model versus a model trained on the entire data set. I'm sure other people have done this looking at it from just the scalability perspective, but it seems like if there's some advantage there just from a scale perspective, and now you're overlaying the privacy piece, that's kind of further supports doing this.
Yeah, that's a very good point. So we haven't looked at the theoretical aspects of this trade-off, but in practice, what we found is obviously if you have the resources, the approach is by definition very parallelizable. So you can train all of the teachers simultaneously, and so you if the resources are there, you don't see an overhead on in terms of training time compared to just training one model. One thing is, even if you have limited resources, because each model gets less data to train from, it also trains faster in general. And so I would say the computational overhead is not a main limitation. It's kind of like the rest of deep learning. If you have lots of resources, it makes your life easier. But in that case, because you're able to sort of prototype your model without privacy, and then once your model is properly fine-tuned and you have all the right number of layers, right hyperparameters, you can sort of apply the pate approach. You know what architecture you're going to go for, and so you just parallelize the training over all of the subsets of data, and so that's relatively straightforward.
Is the implication of what you just said that in practice you're going to want to design your model by training against the entire data set as you usually would, and then apply differential privacy as a kind of a step further towards production, as opposed to designing, from the beginning with differential privacy in mind in a such that you may never train against all of your data, but always do this approach?
Yeah, so it really depends what data you're handling and how sensitive it is. I'm sure that in some cases it's just not possible to train, maybe for legal reasons, on the whole entire data set if you're not able to provide privacy. But what I wanted to basically to say is that if you have about the same amount of data that you would use in a partition, then you can prototype your model and then replicate it over the other partitions. And so that is a very easy and practical way to limit the overhead of implementing the privacy, because you only implement privacy once you have the model that you're confident with that is a good fit for this particular task.
Yeah, can you say that again? I don't think I followed it.
Sure. So let's say you're going to train on 50,000 inputs, and basically once you can prototype your model on a subset of the data, and once you have a good model, then at this point only you have to replicate it over the different subsets of data to train the ensemble and then achieve the privacy. But you can sort of do the prototyping for a single teacher before you train the entire ensemble. I guess that was my point.
Okay. And so then the data sets that you train the teachers on, they don't need to be, it sounds like, strict partitions of your data. They can be overlapping.
No, they have to be non-overlapping.
Okay.
if they're overlapping, then this changes the way that you analyze the privacy guarantees. Because essentially, when they are non-overlapping, changing one point of the training data
has impact in multiple teachers, right?
Right. So if you have overlaps, then you have to, if there is, for instance, a point in 3 partitions, changing that point would change 3 teachers in the worst case.
Right.
And so you have to take that into account in the privacy analysis. So in our case, we always consider non-overlapping partitions. And if you wanted to use our approach and the guarantees that come with it out of the box, you would have to use non-overlapping partitions. You could adapt the privacy analysis to take into account the fact that the partitions are overlapping, but that would probably require more work than the benefit that you'd get from having overlapping partitions.
Okay. I thought that what you were saying previously implied duplicating the data that the teacher sees or overlapping in some way.
Oh, no. Well, I guess I may have said something ambiguous. What I meant is that you can perform sort of the parameter search of your model for only one of the teachers and then apply that search to all of the other models in the ensemble, which reduces the amount of time that you have to spend training the models.
So in other words, instead of training the 500 teachers, you train one teacher and use the parameters for all 500 teachers.
So you use the hyperparameters, like the
number hyperparameters, right?
The number of layers. So once you've found an architecture that works well for this particular data,
got it. Okay, sorry about that.
No, that's fine. It's very subtle because even you have to take into account that every time you use the data that is sensitive, you have to take that into account if you want to provide the guarantee of privacy of the overall approach. So it can be very tricky.
Okay. Any parting words or thoughts on what's next for you in this line of research?
Sure. So I'm extremely excited about this synergy between privacy and utility again. I think that's really a deal breaker. And in terms of the next steps, I think the most compelling would be to apply these techniques to data sets that have traditionally been very hard to tackle with privacy preserving techniques or to get good performance at. To sort of show the implications of these techniques to real world applications. And there is also one thing that I'm interested in.
Before we go there, what are some examples of those data sets that are traditionally difficult?
I mean, there's a lot of progress being made in healthcare, for instance. And obviously, these approaches to provide differential privacy are a good way to address some of the concerns that users contributing these data sets may have. Mm-hmm. There are many examples, even in applications related to justice or anywhere where the data is sensitive, and we're at the same time making progress with applying neural networks or other more complicated machine learning, because differential privacy used to be limited to more simple machine learning techniques like logistic regression, and so now that we are able to provide differential privacy with things like the deep neural networks, it's very exciting because that means we can look at tasks that are much more complicated to solve, and mm-hmm. that means in turn that will have a very beneficial impact on society at large.
Great. Well, Nicolas, thank you so much for taking the time to walk us through this. It is really interesting and important work, and I'm looking forward to kind of tracking it as you and others in the space progress it.
Yeah, thanks a lot, Sam, for having me. I really enjoyed our conversation around privacy.
All right, everyone, that's our show for today. For more information on Nicolas or any of the topics covered in this episode, head on over to twimlai.com/talk/134. Thanks again to our friends at Georgian Partners for sponsoring this series, and be sure to visit their Differential Privacy Resource Center at gptrs.vc/twimlai for more information on the field and what they're up to. Thanks so much for listening, and catch you next time.